Well, as Carol mentioned, I just graduated from WSU last December. I did my research on soil compaction under the guidance of Dr. Haley Neely. We were super interested on, oh, well, I guess I should introduce myself before I go ahead. I am originally from Ecuador. I came first to Purdue and I did my master's in agronomy. I worked back home for over 2 years in a flower company, and I reached a point where I wanted to do more, but I didn't know how. So I felt like I needed to polish my tools and how to do research and be able to find answers to some questions that I had in terms of soil fertility, which is what I was doing back in Ecuador. And right after that, after I finished at Purdue, I moved here to WSU and did my PhD in soil physics with Dr. Haley Neely. So I am super, super excited to share with you all our findings on the impact of compaction, on root growth, physical properties, and besides that, we were also interested on developing a protocol to map soil compaction at field scale here in the Pacific Northwest. So the two crops we focus on for this project was winter wheat and spring canola because those are two popular crops in the area. So the direct measurement of compaction, and you are probably familiar with this, but just in case you are not, I'm just gonna go through over this very quick. The direct measurement of compaction is bulk density. So these two diagrams are just hypothetical representations of a soil before and after compaction. When we press the soil, we bring these particles closer together, increasing bulk density and decreasing porosity, which will affect water storage, root growth, plant growth, among many other soil functions. In the context of agriculture, especially high input agriculture, compaction mainly occurs from field traffic equipment. And some areas like the Midwest and the Great Plains have adopted traffic lanes to reduce the spread of compaction. But as you all know, we are blessed with hills, so you are either going up or down around here. So it's really hard to adopt this technique. Therefore, the spread of compaction throughout the field is really a concern. And beyond that, it's really hard to spot where compaction it has become a problem at field scale because higher yielding areas are probably mask these effects of low yield or highly traffic areas in the field. And in addition to that, we have tried to use yield as a metric to spot those areas that are affected by compaction. However, the effect of compaction under rain-fed conditions really change with weather. Therefore, yield is not a consistent metric to see where in the field are we having problems with compaction. So we decided to explore below ground and try to see if the effects of compaction on root growth were consistent. And in addition to that, we also looked at soil properties such as soil moisture to see what's happening, especially in rain-fed conditions where water is gold. With the input from farmers and historical images, we identified high and low traffic areas, and we installed equipment to collect root images and soil moisture measurements from early spring until before flowering. We also measured texture and nutrient analysis. We did these experiments in 2022 and 2023. The figure to the left left is showing bulk density by depth. The red line represents the high traffic areas at each site and year, and the yellow line represents the low traffic areas. What we found is that high traffic areas have the most compacted layer in the topsoil, which will be the first foot, where these layers in the low traffic areas were below 2 foot. In the figure to the right, I'm showing water depletion. So we looked at water depletion for spring canola and winter wheat throughout the season for each site and year. And I should say that the orange line are the low traffic areas and the blue lines are the orange line are high traffic areas and the blue lines are low traffic areas. So the main takeaway from this figure, or what we found, is that low traffic areas have more water depletion than high traffic areas. Therefore, it's telling us that we have water in the field that is not being used by the crop. And I'm going to elaborate a little bit more on that on my next figure. So this figure is showing root growth for spring canola at the top by depth and winter wheat at the bottom for fine roots, intermediate roots, and thicker roots. So in summary, across both crops, what we found is that root length decreased by 40 to 97% with increased traffic. For canola specifically, only fine and intermediate roots were affected, where for wheat, all root diameters decrease with increased traffic. From a separate analysis, we identified that 9 to 42% of these changes in root length was associated with volumetric water content or soil moisture. So overall, in areas where we have more water, we found less presence of roots, probably due to restricted root growth in those compacted soils. In terms of yield and yield quality, high traffic areas develop undesirable traits for both crops. For example, for yield, we saw a decrease by 16% in yield. In terms of residue, it decreased 12 to 18%. And it also developed undesirable traits such as increased grain protein for both wheat and canola. For canola, specifically, we saw a decrease in grain oil by nearly 4%, and for wheat, a decrease in test weight by around 3%. For the second or a separate project, we wanted to develop a protocol to map compaction. Although bulk density is the direct measurement of compaction, measuring bulk density at field scale is not really feasible due to time. So we explore other measurements that are easier or faster to obtain and use those to predict bulk density by depth and across the field. To do that, we started with a survey for electrical conductivity. From this survey, we collected a map and selected points, 12 to 18 points at each field from where we collected penetrometer readings and soil cores to measure bulk density and soil moisture. There we go. So the first step was to do predictions in the soil profile. And we did that by using force, depth of insertion, and soil moisture to predict bulk density. This figure is just showing an example of how these predictions look like by depth. And from the results, we first put all the sites together because ideally we want the same data set to use to work across all fields. I forgot to mention where these fields were located. We had 2 fields at Davenport, 2 fields at Fairfield, and 2 fields at Bickleton near Prosser. So we had them all together. The model did not perform very well, and all these metrics really improved when we separated these models by site. And the models work very well at 2 of the 3 locations. The driest locations near Prosser was the one where we were not able to do predictions using this model that I showed earlier. And we had little variability in bulk density to begin with. So that was probably the reason why it didn't work. And the next step was to do predictions in the landscape. And for these, we explored several metrics that are easy to obtain, including electrical conductivity that we collected early in the season, several features from digital elevation models, and vegetation indices at 10-meter resolution that were averaged by month. The 2 vegetation indices we selected were based on previous research, and these indices were EVI and NDMI. This table is summarizing the features that were more important for the 2 locations where the models perform very well and are listed in order of importance. These numbers represent the percentage of importance for each depth. As we can see on this table, different features were relevant at each location. The main takeaway from this table is that the vegetation indices for mid-May and end of the season were relevant covariates with bulk density, as well as electrical conductivity and terrain wetness index. The value of this step is that all these features are available to the public. This is a summary of the predictions done by depth in the profile. And to the right, we have example of maps from our predictions showing bulk density predictions in space. There is more to do on this project. One of those things is increasing the number of samples to improve or reduce the error of these predictions, and also explore the use of terrain attributes to select those sampling points instead of electrical conductivity, especially those attributes from vegetation indices from mid and end of the season that seem to be highly correlated with bulk density. So, a quick overview from my project. We found that traffic has detrimental effects on bulk density and soil moisture, and which in turn is going to affect root growth, access to water, and at the end of the day, it's going to affect crop yield and yield quality. Also, these decreases in root growth as compaction increase is probably going to affect nutrient cycling and carbon sequestration. And therefore, we suggest to look more into that, especially when we think about grassland and agricultural land being responsible for nearly 50% of carbon sequestration. And the newly developed protocol can be used to detect critically compacted areas, as well to evaluate the effectiveness of management practices at field scale. With that, I'm going to leave my contact information. I will be happy to answer any questions now or later. Feel free to reach out. Thank you.